Dear students, this is our 26th lecture in medicinal chemistry and fourth lecture on antibacterial drugs. Uh, in the earlier three lectures, what we have discussed is that what are antibacterial drugs and what is their mechanism of action in lecture 1 and 2, about how the antibacterial drugs they act on the bacteria through cell wall or cell membrane or ribosomes or nucleic acid. So different categories of antibacterial drugs have been discussed in lecture 1 and lecture 2. In the first lecture, we have discussed about inhibitors of cell wall synthesis, how antibacterial drugs they can inhibit the cell wall synthesis in case of bacteria. Whereas in the second lecture, we have discussed how antibacterial drugs they can be affected by inhibiting the protein synthesis or cell membrane synthesis or nucleic acid synthesis or metabolic pathways in case of different types of bacteria. Then in the third lecture, we have discussed about synthesis of few commonly used antibacterial drugs like furazolidine, zolidone, nalidixic acid, ciprofloxacin, norfloxacin, dapsone, 4-aminosalicylic acid, isoniazid, ethonamide, and ethambutal. So we have discussed about the industrial synthesis of these commonly used antibacterial drugs. Now, in the fourth lecture, we will discuss a few more antibacterial drugs like this most commonly used antifungal drug, fluconazole. There are several novel methods for the synthesis of fluconazole which have been quoted in the literature, and some of the important ones we will discuss over here. And these three methods, they are: first method is conversion of an epoxide into fluconazole. Then second method is lithiated or Grignard difluorobenzene is converted into fluconazole. Then third, we will discuss some commercially viable methods for the synthesis of fluconazole. So first is how an epoxide can be converted into fluconazole. The fluconazole produced by this method is formed in about 44% yield, and we start the process from 1,3-difluorobenzene. When this 1,3-difluorobenzene is reacted with chloroacetyl chloride in presence of anhydrous aluminum chloride, you know, this is a method of Friedel-Crafts reaction. So electrophilic aromatic substitution on this aromatic compound will take place. In presence of anhydrous aluminum chloride, this chloroacetyl chloride will give us carbonium ion, and AlCl4 negative will be formed at this place, and we will get this product through electrophilic aromatic substitution reaction. And then this will react with this compound prepared will react with the triazole in presence of this triethylamine. Basically, nucleophilic substitution reaction will take place. This nitrogen will act as a nucleophile and attack this carbon with the elimination of this halogen. So H from here, Cl from here, we will get this type of triazole derivative. Then in presence of trimethyl sulfoxide iodide, this sulfonium gyrate, this will form a this will convert this ketone into an epoxide, and then this epoxide again will react with one more molecule of triazole in presence of potassium carbonate. Again, this will act as a this nitrogen will act as a nucleophile, and this will attack the less substituted carbon of this epoxide. This carbon is more substituted, this carbon is less substituted, so less hindered carbon will be attacked by this nitrogen. With the breaking of this carbon oxygen bond, this nucleophilic addition at this carbon will take place, and this will be converted into fluconazole. So this is how an epoxide can be converted into fluconazole. This is very common method for the synthesis of fluconazole. Then lithiated or Grignard difluorobenzene to fluconazole. Here again we will start with this aromatic compound. Uh, in the first step, we will either synthesize Grignard reagent when this is reacted with magnesium in THF, or isopropyl magnesium chloride or lithium chloride is reacted to give us this type of uh, lithiated Grignard reagent as the intermediate. And again, this Grignard reagent will react with this dichloroacetone. 1,3-dichloroacetone is reacted with this Grignard reagent. 2,4-difluoro benzene magnesium bromide. This is reacted with 1,3-dichloroacetone, and we will get the corresponding. We know the ketones on reaction with Grignard reagent, they are converted into the corresponding alcohols, and then this alcohol, chlorinated alcohol, will react with two molecules of triazole. Again, one will attack here as a nucleophile, with chlorine being the leaving group, and again second molecule of triazole will attack this with the elimination of halogen, and we will get fluconazole as the product. Then third is the commercially viable method. Here the fluconazole is formed in higher yields in comparison to other methods. Again, this starts with the same 1,3-difluorobenzene. This will undergo Friedel-Crafts reaction in presence of isopropyl alcohol in sulfuric acid or AlCl3. We know in sulfuric acid this will be converted into a carbocation, and that carbocation will undergo lactophilic aromatic substitution reaction to give us this type of 2,4-difluoroisopropyl benzene as the product. Then this intermediate will undergo bromination either in presence of bromine or N-bromosuccinamide. So we will get the corresponding bromine will be added to these two carbons. So this dibromo derivative will be formed. Then this on heating at 80 to 100 degrees centigrade in presence of sodium acetate acetic acid, dehydrohalogenation will take place at this. H from here, Br from here, a carbon-carbon double bond will be formed. And this intermediate on reaction with N-bromosuccinamide in acetic acid will be converted into the corresponding acetate. So ester will be formed at this place, and we will get this type of dibromo ester as the product, and then again this will react with two molecules of triazole getting attached to this carbon and this carbon by nucleophilic substitution. Br from here, H from the triazole, we will get replaced by 1. Then another molecule attacking here, Br from here, H from here, another molecule of triazole will be substituted at this place. And then hydrolysis of this ester will take place to give us the corresponding hydroxyl group. So this is how fluconazole can be synthesized commercially. Then next is iconazole. This again is an antifungal drug where instead of triazole we are having a imidazole series attached to this. So this was patented in 1968 and approved in 1974. So iconazole is synthesized by alkylation of imidazole with this bromoketone 2,4-dichloro uh, phenacyl bromide. So this 2,4-dichlorophenacyl bromide on reaction with imidazole in presence of triethylamine is converted into this type of ketone product. So basically here also imidazole will act as a nucleophile. Nucleophilic substitution will take place. This will attack at this carbon. Carbon-nitrogen bond will be formed with the elimination of this bromine. So Br from here, H from here, HBr will be eliminated. Triethylammonium bromide will be formed, and we will get this type of substitution product. And then this ketone will be reduced with sodium borohydride, the corresponding alcohol or hydroxyl compound will be formed. Then this hydroxy compound reacts with this bromide derivative. So Br from here, H from here, we will get the this thing. Corresponding benzyl ether will be formed, and this will lead to the formation of through alkylation iconazole is formed as the product. Then is griseofulvin. Griseofulvin is basically a natural product. This is an antibiotic produced from this fungi Penicillium patulum. This act as a antifungal agent. Uh, this is an optically active compound, but most of the synthetic methods which have been used for synthesizing this antifungal drug, they have reported to yield the racemic mixture. So first method for the synthesis of optically active natural enantiomer of graciofulvin, and this was achieved when we started from dimethoxyphenol. So when dimethoxyphenol on chlorination with SO2Cl2 in presence of acetic anhydride pyridine, the chlorination will take place at this carbon, and we will get the corresponding acetate chloride because this hydroxyl group will react with the acetic anhydride in presence of pyridine to get converted into the corresponding acetate derivative. So 2-chloro-3,5-dimethoxyphenyl acetate is formed as the product, and this intermediate undergoes Fry's rearrangement to give us this type of orthohydroxyacetophenone derivatives. This orthohydroxyacetophenone derivative on Mitsunobu coupling with R-pentene 3-2-ol, R-pent-3-ene-2-ol will lead to formation of this uh, S-ether. So this ether then undergoes reaction in presence of Mander's reagent to get converted into beta ketoester, which reacts with macetyl nitride, macetyl azide to give us this type of diazoketone intermediate. And this diazoketone intermediate undergoes decomposition in presence of 5 mole percent of rhodium pavylate catalyst, and this undergoes sigmatropic rearrangement to give us this type of product through cyclization and elimination of this diazonium salt. And then this cyclic product, which is formed in 62% yield after purification, is converted into methyl ketone derivative. This methyl ketone derivative is formed on reaction with this carbon-carbon double bond, and this methyl ketone derivative then through Dickman cyclization is converted into graciofulvene as the product. So this is how optically active graciofulvene was synthesized by Purig and William L. Brown in 1990. The next is chloroquine. Chloroquine is primarily used to treat malaria, but this has also found a good inhibitory effect in case of COVID-2 virus. This was first synthesized in 1934 at Bayer, and then in 1952 by William Johnson optimized the synthesis of this biologically active compound. So more recently it has been synthesized starting with 7-chloro-4-hydroxyquinoline. When this is reacted with phosphorus trichloride, phosphorus oxychloride, then basically this hydroxyl group is converted into a chloro group. So 7-chloro-4-hydroxyquinoline is first converted into 4,7-dichloroquinoline, and then this is condensed with 4-diethylmino-1-methyl-butylamine to produce chloroquine as the product. Similarly, this can also be synthesized from this compound. So 4-bromo 7-chloroquinoline can also be used for the synthesis of chloroquine in presence of palladium acetate and other reagents which are same, that is 4-diethylamino-1-methylbutylamine. When this is condensed with this 4-bromo 7-chloroquinoline derivative under these conditions, this is converted into chloroquine. Then is primaquine. Primaquine is synthesized from 4-methoxy-2-nitroaniline through group synthesis reaction. So when in the first step the glycerol is reacted under sulfuric acid conditions with this reagent, this is converted into quinoline derivative through group synthesis, and then this 6-methoxy-8-nitroquinoline derivative undergoes reduction in presence of tin HCl. This nitro group will be reduced to amino group, and this 6-methoxyquinoline 8-amine then condenses with this bromo derivative 2,4-bromopentyl 1H isoindole 132H diol. This reacts with this quinoline 8-amine. So this will act as a nucleophile, will attack this carbon with the elimination of bromo from here and H from here. We will get this type of methoxyquinoline derivative, and this methoxyquinoline derivative then react with hydrazine to give us primaquinone as the product. So this is how the primaquinone is synthesized through this method. So these are the references which have been used in preparing this lecture. Thank you very much.